let's go back to the notes after last class with slides. And I had an example to do of a nonlinear equation. And then I'm going to show an application which resembles something we saw in the slides. Okay, so first as an example, I will not do all the details. I recommend you try to do it on your own, and then there's details in the notes, right? It's a good sort of exercise you don't have to hand in. So a nonlinear, let's call this example this, a nonlinear wave-like excuse me, equation where we have this equation. It's an initial value problem f x t u q equals to zero. Let me put this here. A greater than 0. Excuse me. So, written like this on purpose. Why am I calling it a wave-like equation? I mean, I confess I don't know exactly an example for this, but we could find. I mean, it's if we write it like this, it looks like okay. Maybe we can find an example for this, which is if I write it like this. Okay, so it looks like a wave equation, but now it's nonlinear. It's not semi-linear, it's nonlinear. And we can think of the propagation speed instead of like Burger's, which was u, now it's u of x. So it's the slope that sort of controls the speed. Okay, there are problems which, actually I know it's not the equation not like this, but where the slope, maybe at the very end of the course I'll show you a problem of a bouncing droplet. Maybe not, I'm not sure. I show it in the fluids course, but where the slope of the wave is what dictates the speed. Okay. So, right, so we have that f is equal to q plus p squared, right? Because this is playing the role of y. So let's try to solve this problem. Okay, I won't do all the details as I said. Let's try to solve this problem. The solution, excuse me, kind of the characteristic equations are simple. Everything is kind of simple, but the dynamics has a little bit of a different thing, and that's what I'll point out very briefly. Okay, so if we parameterize our initial value problem, right? We have this. Let's say I'm using z. Yeah. Okay. Excuse me. The air conditioning these days starting to get to me. So now we have this condition. Right, we have a name for this condition, the strip condition. And this strip condition, right, that we saw, it's sort of easy to solve. And this will give us, let me put it like that. As I said, I will not do everything because it's very simple. We got that P of S is A, Q of S is minus A squared, right? Just plugging in these guys here. Very simple. Let's see, it saved the blackboard. I gotta always be thinking about this because it's good for the video to stay in the same blackboard. So we have the characteristics equation. I'm gonna write it like this. Let me just copy so I can move on fast. 0. Okay. And then we will conclude. Okay, so skipping a few points. Right, it's a good exercise for you to do, simple exercise for you to do. Having the solution is that u of xt is equal to ax of at. Okay, you got to this. So it looks like a simple looking solution, something translating to the right with the speed that was given and the initial condition. Okay, and the last thing I want to point out to you, without giving all the details, is try to convince yourself that we have a picture like this. It's kind of fun, right? Because it looks very simple. So if I put here u, I put here x, okay? So look, if I put here u, and excuse me, I think I have to drink some water soon because the throat getting dry from the air conditioning. So what is this orange line here? Initial condition, very simple, right? So very simple. And then if I put another line here, right, this guy moving. So in the notes, okay, what I'm showing to you in the notes, and I'll do it even less here, so that you stop and think and try to do it on your own, right? It's a good exercise. Soon I'll be giving you maybe more problems, is that we see something like this. If I have a point that started here, right? This looks like a very simple kind of wave moving that way, something translating that way. But the interesting thing is that this guy that was here, later on, he's here. So convince yourself, okay? Using the characteristics, don't try not to look at the notes, and see that at time 0, the guy here, and here I'm saying this is at time capital T, and see that the point that was here, okay, is not on the same line. It actually starts going up the profile. So it looks at first like a very simple dynamics, just a linear profile, right? The slope moving this way. It looks a little boring, but there's more to it. Like the points are sort of climbing the profile. Okay, convince yourself. So here, of course, I'm not explaining it right. I mean in detail on purpose. Okay. Good. So I finished the example in this blackboard, and now I'm going to go to maybe our first kind of more applications of the course, right? We did all this in sort of an abstract setting, blah, blah, blah. So let me go with something which will remind us a little bit of the problem, that very complicated problem that we have to do in the computer, which is the Mahmouzi profile. So if you remember from last class, we had this very colorful thing, which was the crust of the Earth with sliding profiles and so on, right? So we're going to see the equation that actually was being solved on the computer. The things that problem, the coefficients were crazy, right? I mean, okay, so 2D, look at this. In this problem, I think it's fun because we start with a 2D wave equation, linear wave equation, a problem that actually, in principle, will be easy to solve to some extent, but it gets complicated because of the variable coefficients. And the surprising thing is that we're going to do some asymptotics, first sort of exercise in asymptotics, and from this linear problem, we're going to extract a nonlinear problem, which is the diagonal equation. So we're going to see how the diagonal equation comes out of this, okay? So that's the advertisement of what we're going to see. Okay, so let's go. So let's take a 2D wave equation, and I'm going to write like this, because I'm going to be changing variables all the time. in a heterogeneous medium. So similar to the Mahmouzi picture last class, right? So we have a 2D domain, wave equation, just written with the C here instead of over there, right? And here's the Laplacian. And actually, we're going to learn how to solve for constant coefficient. It's very easy. Excuse me, I have the water. It's very easy to solve this 1D problem. So if I hide this, we can get an, and this is constant. This is very easy. It's the famous D'Alembert solution, right? We're going to see how to do that. It's very simple in a few classes. But here the idea is that I want to show you is let's start playing with scales, with a little bit of asymptotic kind of thinking, and do modeling, extract from a complicated problem something that looks a little more simple. And it's not going to be that simple because it's going to be the Eichhorn equation, then we're going to make it even simpler. Okay, so look at this. How does one think of a problem like that, right? So maybe I should do a picture. Let me do a picture here. Okay. My coefficients could be varying like this. Okay, my layered medium, I send in something here, okay? And I want to see how the wave propagates. Of course, this is very difficult. And in principle, this wave is going to be something like that, right? This is just schematic because of the variation of speed. It would be already deforming. So this is really a caricature, right? Very schematic. And maybe at first, too, this is a bit of, it's just to motivate, but let's think for the moment that C is smooth. Here, the speed is not smooth. It's constant by parts, right? But let's think that the speed is smooth, okay? And let's think that the wave is a time harmonic wave. So what is a time harmonic wave? The name harmonic comes usually in different flavors, right? If somebody tells me harmonic, what do I think? I think, well, either that person is thinking about Laplace's equation or harmonic function. Well, we haven't seen that yet. Or the person is thinking about something oscillating in time. That's actually the first thing I would think, because what is the harmonic oscillator? It's like that mass spring, you pull it, and it oscillates, right? So harmonic oscillator. So that's what I think. So something that's called time harmonic is this. So let's do the time harmonic case or wave. And this is also a good example you're going to see me doing all through the course. Like, somebody gives me a difficult problem, right? I'm going to be using this German word that we also use in applied math called an Ansatz. I'm going to write, which is basically like an educated guess. You write the Ansatz, you're already telling the reader or your audience what you're thinking of, what kind of solution you're looking for. And you're trying to sort of see if it works, right? If you get into something that obviously there's not a solution does not exist, or whatever, you say, oh, I've chosen a bad Ansatz. But then sometimes, and here, it's not even an Ansatz. Here's like, this problem is complicated. So let me start with as simple as I can of a situation. So what is as simple as I can? Situations that in time, something is a little bit prescribed. It's going to be oscillatory in time. So time harmonic wave, now the good way to tell my audience, you, what I'm thinking is saying, look, I'm going to write this. Capital V, right? So here I shouldn't take these little legs here, just to make it sure. Capital, oh, it has the little one too, doesn't matter. Capital V is now this. Okay? So what I mentioned about a time harmonic case, which is a simpler wave that is oscillatory in time, and instead of putting a sine or a cosine, the problem is let me put the exponential, which is easier to manipulate, because if you differentiate it, it becomes an exponential. So So this is a fancy way of saying, for this case, that I'm going to say in different ways what I just said. I'm going to do a separation of variables, time and space, right? Another way. Or another way of saying the same thing, which is the time harmonic, which is exactly the same thing. Let me try to see if things work with a sort of a Fourier mode in time, because I could also use Fourier mode in space. But Fourier mode in space is not a good idea, because it's variable coefficient in space, okay? So, right, things are gonna, so this is what I'm doing. So this says, okay, somehow I'm forcing this system with something which is periodic in time, time harmonic. Let me see where this equation takes me if I put, now I could even call this an ansatz, but it's too much of a word, right, for this. I'm not saying much. Okay. So if I put this in the equation, we get another famous equation. We get this is a PDE course, so it's good to learn these names. We get a Helmholtz equation. Okay, the Helmholtz equation is like this. Now it's a capital V, capital Y. I'm already changing. I got to explain my notation. I'm already putting things together because it looks interesting. So I went from one equation I went from a time-dependent equation to a time-independent equation because I simplified the dynamics in time, right? So that's what I do. I'm pretending I've never seen this problem. Let me try to simplify it to see where I can get, right? So I removed time out of the problem. This is the Helmholtz equation, and sometimes it might even look like a little bit like if you put this on the other side, it could look a little bit like an eigenvalue problem for Laplace equation, but then the signs, but okay, not getting to that. So what is this Kn? Okay, so Kn is this. So you may ask me, right? Where is this coming from? Well, this is just reorganizing things. Of course, this depends on the speed because the speed disappeared. But this is because, as I'll show you, n is I'm going to call it the index of refraction. So this I'm already preparing the equation to do geometrical optics, even though I'm using seismic waves or acoustic waves in the crust of the Earth. Okay, but we're going to use ideas of optics. Okay, so let's get the notation right. It's important to get the notation. So this is called the wave number. We're going to be using this all the time, where this is the wavelength. Whoops. Okay, and omega is the angular frequency. Because t is the period. Okay, so basically, we're going to be using, you're going to be seeing in the future many problems, K and I'm thinking because of my notation. Okay, K here, it would be, I didn't write this, I only noticed this now, but it's basically K would be the absolute value because this is the wave. Let's see how I do this so I don't get you confused because of the notes. So this is because I have two directions, X and Y. So if I were in only one direction, one dimension, K would be this, and this is the period in one direction, this is in the other. So it's not well written. So let me put it like this. In 1D, because I only noticed now my notes are not very good. So in 1D, we write it like this. In 2D, this will appear later on, but I think my notation is bad here, is that we have a wave number vector, okay? So let me leave it like this. In 1D, and actually, let me then write the drawing I have later on, but let me put it like this. No, let me do it like this. Let me fix it. So if I have a wave like this, right? So let me fix it because I think that doesn't really matter, but this is the wavelength, okay? So if I take a photograph of my wave, this is the wavelength, and k, the wave number, gives me something like a spatial frequency. Okay, because it tells me over 2 pi how many lambdas I have, right? On the other hand, this angular frequency here is a frequency in time, where it's obvious from here, right? And of course it tells me over 2 pi in time how many periods I have. So that's the angular frequency. Okay, so so what has been done here? So for the 2D case, we can think that actually k is the same as the absolute value of the k vector, which is square root of k1 squared plus k2 squared, looking at the periodicity in each direction, okay, if it's 2D. Right, it's here written in the notes. I didn't even use the modular. Yeah, it's okay. So it's, yeah, that's written in the notes over there. It's a little bit poorly explained. Now, we now call n of xy, it's called the index of refraction, just like in optics, and it is defined as omega over kcxy, which is then the same thing as c naught over cxy, because omega over k is called the phase speed. Did I write here in the notes? No, I don't think I did, but it doesn't matter. Okay, so let me motivate this to you, because I think this is a little more like with a physics flavor, but in the mathematics. So, as I said, this n comes as index of refraction. So index of refraction is basically related more to this. Look. Why? Because the C0, we're going to call this we're going to use this later on a lot in asymptotics, some reference numbers. So think that C0 is a reference speed. So it's like a typical speed of an acoustic wave, okay, in this region. But the speed might be varying because of different materials. So the index of refraction is a ratio, so this is a little bit from physics, right? It's a ratio of the reference speed of something in the medium, right? Would be a ray of light, either in the air or in the water. And you're going to see that the rays here are the characteristics, okay? So this is a ratio, right, between the reference speed and the actual speed at that point, which is varying as the wave is moving, right? So this gives you the index of refraction. And this is just obtained by, you plug this in, you're going to differentiate in time, you're going to get omega squared, blah, blah, blah. That's why you get the n squared. You multiply and divide by k, blah, 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 and that's how you get this guy. But this guy, to look more like optics, you write it like this. Oh, you write it like this. What is the reference speed? The reference speed is because I'm picking a reference wave number, therefore a reference wavelength. I tripped on my tongue, right? Reference wavelength. Therefore, that gives me a reference wave number. And omega naught is basically this, omega over k, phase speed. So why this is called a phase speed? Because you will see in problems in the future that instead of it's convenient sometimes to write a Fourier mode like this. So this is a generic. We'll be using this in the future. Right? This is a generic Fourier mode that's traveling to the right. No, what do you mean by that, André? Look, it's simple. Pull this k out. Right? And this is the C0. So this is a Fourier mode that's at time 0, it's e to the I kx. Right? So it's something that looks like this in space, the real and imaginary part. One is a cosine, the other is a sine, right, from Euler's formula. And this then is a generic Fourier mode, which is traveling to the right with the speed c0 to the right if c0 is greater than 0. And this guy, we're going to check, test, verify properties of certain PDEs, linear PDEs, constant coefficients later on using this guy. And it's going to give me something that's called the dispersion relation, which is the relation between the time frequency and the spatial frequency. And you're going to see some problems, some PDEs, when you do that, the PDE, which is a differential equation, becomes an algebraic equation, easy to solve. Okay? This is like advertising something in the future. So therefore, coming back here, right, it was, at the beginning it looked like a lot of information for you. Let me rewind the tape because you're going to see it's simple. I have this complicated equation with a variable coefficient in space. So it's very difficult for me to say what is going to be its variation in space because it's changing all the time. But because this problem is difficult for me, it's new for me, I'm going to say, well, let me see if I can get away as a first study of putting a simple variation in time and see what are the consequences in space. Here it goes. I put this in, out comes an equation that's kind of a known classical equation, Helmholtz equation, but with a complication, a variable coefficient. Right? This variable coefficient, it's written like this because it sort of brings our mind into things like from optics, index of refraction, blah, blah. That's all. And this is just rewritten this way by manipulating like that. And the most important thing is to notice that this basically says that we have a reference k times index of refraction, which is a ratio between two speeds, a reference speed and the speed that's happening. Okay, but this is still difficult to solve, right? We made a move. We went to solve a simpler equation, but it's still difficult to solve. Okay, so let me see what I want to do. The things that I mentioned about. Yeah, I think I'm okay. I didn't forget anything. But now, let me drink a little bit of water before I start. Now I say, well, this is still complicated. So let me look for a special wave regime. Okay? The special wave regime, let me make this drawing again, is going to be like this. Which is the regime for geometrical optics. Special wave regime that sort of connects with geometrical optics, let me write it, that inspires this. That motivated this presentation, let's put it that way. Okay, so the wave, if I think now of water waves, so let me go to my field or so look, now I'm talking about almost like 3 applications altogether. The motivation started from, say, acoustic waves in the earth. We're using ideas from geometrical optics, and I'm going to show you also in terms of my personal field of application, which is water waves, the analogy, how all these things work. Okay, so suppose that this is the bottom of the ocean, this is the depth, and as I mentioned to you, for tsunamis, right, the water wave speed decreases with the depth. Remember I mentioned to you that tsunami, when it gets close to the coast, it slows down. You will see this later on in the course, something that we definitely see in all details in the fluids course. Okay, so if I put a Fourier mode, so like a wave that's traveling in a slowly varying region, so these are all terminology we're going to be using over and over, either fast varying or slowly varying. So bottom of the ocean, let's consider the slowly varying case. That's not the case of the Nazaré waves we saw, right? There was this canyon that suddenly changed a lot. A slowly varying case is, as the name says, very slowly, but with respect to what? Slowly varying case. So it's slowly varying has to be with respect to something, with respect to the wave, which means that this length scale here, which is, say, the lambda of the bottom, okay, is much bigger than the lambda of the wave. Right? If I say something's rapidly varying or slowly varying, right, I could say the wave is rapidly varying with respect to variations of the medium where it's propagating, or I can say the other way around, the medium is slowly varying, okay? Just terminology. Now look what happens. Look what happens. In this region here, so let me draw this like this. This is the undisturbed, think of this as the undisturbed surface of the ocean. There's no waves, okay? And then this periodic wave comes, right? It's coming. Since it's periodic, it should be everywhere. Let's think of it everywhere. But I'm drawing it in pieces. So if it has this speed over this deep region, here, it's more shallow. So since here it's more shallow, the speed is going to go down, we should have what's called a wave modulation. Can you see what I'm about to draw? Which means it's an effect that sometimes I call a little bit like an accordion, right? Sanfona in Portuguese, an accordion. Like you pull it out, you pull it in. Why? Because this wave train here is going to move slower. So the picture should be something a little bit like this. Look. Do you agree? Right? Because this wavelength here is going to be lambda, let me call it, bar smaller than the other one. Because if the wave slows down, then, right, it's just like, say, in a train, we call it the wave train. When the locomotive brakes, because of the momentum, right, the wagons tend to pile up. Of course, they don't pile up, but things move forward. So here, what I'm preparing you to see is what the Icono equation is going to do is we're going to control a little bit the phases. So this is the same phase. You see? If I think of this as cosine, as a cosine wave, these are all the points where the cosine is equal to 1. So it's 2 pi m. Right? It's 2 pi m. Because when m is 1, 2 pi. When m is 2, 4 pi, and so on. Right? 2 pi m. And this fact here is a modulation. So at one point we're going to see, actually I showed to you last class, where I saw that the Schrödinger equation for the wave was an amplitude modulation. So let me draw the picture here because it's good. So for the Schrödinger equation, because these are things that's good to have in our minds. For the water wave, this is AM. A little bit the same names we have in radio, AM. Amplitude modulation. Why? Because the wavelength is constant. It doesn't change. But the amplitude is changing. And here is FM, which is frequency modulation. The amplitude is the same. My drawing is bad, but the amplitude is the same. But the frequency is changing. Okay? So these are different effects of waves, depending on where they are, depending on how they're generated, depending on how their dynamics. So now we're going to prepare ourselves to, okay, because this problem here is very complicated, right? And I assumed for a beginning that we had a sort of an exponential, that is a time harmonic wave. Now I'm going to say, okay, the problem is still complicated. I made maybe some progress. I removed time from the problem in a correct way, in an educated way, in the sense by my education in PDEs and waves. But now I'm still in a complicated situation because I have this variable coefficient Helmholtz equation. So now the word ansatz comes into picture. Okay, so now we have an ansatz for the, let me write it here in yellow to call attention, an ansatz for the short wave regime. Okay, remember, I can call this either a short wave or this a long bottom. I can call this a rapidly varying wave or a slowly varying bottom. The words are not important. What's important is where the epsilon is going to appear, right? Of something big respected with something small, right? This is something we're going to learn and practice. Okay, so what is a shortwave regime? Is this. Mathematically, this is a shortwave regime. I'm going to do K big. Mathematically it means K big, right? Because K is big because lambda is small, right? Remember that K is 2 pi over lambda. Okay, so what is the consequence of this? Is that the ansatz, I'm going to even continue with the yellow to call attention, is that I'm going to now say I'm going to do another change of variables. And I'm going to say that my capital V, okay, is actually this. Let me write down. And this is a nice, very nice ansatz that's going to lead us to the Eikonov equation. And let's read this ansatz in words, in English, right? Mathematically, if you've seen this before, I wouldn't have to say anything. But whoever wrote this is telling us what is the next attempt mathematically in the modeling to do. So again, this course is a lot about modeling. What is modeling? Is choosing your mathematical object of interest, which you're going to do your study. And it's got to be well motivated by the application or even just sometimes just mathematically. So this is saying that my solution of the Helmholtz equation, okay, I'm going to do now another trick. Now it's not quite a separation of variables because I have x and y here and I have x and y here. That's all x and y. But this tells the reader, right, if he already seen this before, something interesting. What is he saying? He's saying this is the amplitude of this wave, right, which I'm allowing it to vary in space. So a variable amplitude, let me put it this way, that's a good way of saying it. Okay, and then comes the most important guy here, which is going to be the guy who's going to come into the Eikonov equation. And this is called a phase. I don't know if the red appears well in the video. Let me put it like this. Why the phase? Because if I'm able, think of this. If I have this expression, let's think of this. If I have this expression, okay, and let's come back to this picture here. Okay, look at this. If I have this expression, and I try to look for the level curves, let me say it in word, then I'll go back there. Look for the level curves of Cxy equal to 2 pi. These could be, for example, these level curves here. And maybe varying here, which are the crests of the waves. Okay? And then if I look, I want to see the level curves of Cxy equal to pi instead of 2 pi. Then that's the troughs. That's where the cosine, the real part of that guy, right? I'm drawing the real part. You're not confused, and then I would have to draw the imaginary part, because e to the I something is cosine something plus I sine something, right? So if I think of just the cosine, I'm drawing the cosine. These are the curves where cosine equals to 1 for that crazy function that might appear there. Okay? So that's the level curve. And that's what the icono is going to give us. It's going to give us an idea of where the crests, the fronts of the waves are, right? If I choose a level curve for psi. So here's this psi. So that's why it's called a phase, because its level curves tells us, won't tell us the amplitude. And you're going to see when we solve the icono equation, I'm going to say, okay, this problem is so complicated, I'm going to give up for the time being, because else we have to work much more. I would just indicate that to find the amplitudes. But if I solve the icono equation for this guy, I have that picture of where the wave fronts are, and that beautiful picture that appears in the Mahmouzi thing that was done computationally. But those are the fronts. We don't know what the height of the wave are, but we know where the fronts are. And if we compute the characteristics, we know what the rays are doing, and we can find caustics. But then if you just do it straightforward, the characteristic method breaks down. You got to do more tricks. Okay? So is it clear what this phase function is? It's something complicated. We have to solve a PDE for it. But the level curves, right? A level curve is this, right? Let me just write here. Because again, I have to be a little more careful because we want to keep this in the video. Level curve for the phase is basically this. Right? And for example, in the case of just a point source in a homogeneous medium, right? If you throw a stone in the water and you solve for the phase, these are the level curves, right? Where if I put here, this dotted line means that if I cut here, I'm seeing something like this. Where this is the dotted line and this, right, the straight lines. Right? Is that clear? Right? If I throw a stone and I do this cut here, I'm basically, so I put it this way. This point here is here. This point here and this point here are here and here, depending on which phase I choose. So the level curve for the crests are the solid lines. The level curves for the trough are the dashed lines. So you see, this picture here is like an airplane view, as I mentioned last time, of the wave, right? Because the way the sun shines on it. Is that clear for everybody? Okay? All right. So now it's just using, cranking the wheel, right? So we're going to plug, what we're going to do now is we're going to plug this in. Okay, star into Helmholtz equation. To get the following. Okay, it looks more complicated, right? Now it looks like, what do I gain with this, right? So you could complain, André, come on, what do I gain with this? And one observation here, right? No approximations have been made. This is exact, just plugging one thing into the other. So from there to here, it's just plugging one thing into the other. Okay? I mean, but then at this point it looks, this is getting ugly. This is getting more complicated. Why? What is the good of this? Well, look now. If, with our main hypothesis is this. Remember, short waves. So this is the same as saying that 1 over k is very small. So call this, right? So call epsilon 1 over k. And now this is going to be I epsilon. This is going to be epsilon squared. Right? So this just notation, but as I said many times, mathematically it's very useful to put the best notation to click the idea, right? Sometimes just change the notation. So look at this. So in the language of asymptotics, this is the leading order term. Just like in the Taylor series, right? Leading order term. And these are corrections. The first correction if epsilon is small, and the second correction. Right? So if I solve, so to solve the whole thing is complicated, right? In Zoder, he mentioned a few things, some of the books about the second equation. We're not going to get into that. For us, the interesting thing is this. The leading order term gives me that if this has to be, let me also say one thing I almost forgot, which I think pedagogically is good. If I have something like a Taylor series, a truncated Taylor series, or maybe better to say, which is the correct thing to say, because that's the terminology we're going to use. If I have a truncated power series, okay, we're going to try ansatz many times using a power series approximation of the solution. If I use a truncated, well, here I didn't even truncate it. It's naturally truncated, power series. Well, if this is equal to 0 for any epsilon, arbitrary epsilon, that means each term has to be 0 if I don't make any approximation. So our approximation, let me put it like this. Our approximation is to consider only let me put another name which is useful, the dominant term, which is the leading order term, to get the Equano equation. Okay, so I'm going to be happy to solve the whole thing is complicated. I'm going to be happy solving the Equano equation because I can get this picture of what the fronts are doing in propagating. Okay? And a few comments. I think I can do it in this blackboard. So let me put it here. The Equano equation for the phase. Now, note, let n equal a constant. Okay, and let A also be a constant. Just so we can get a better feeling for what I just said before, and I said a little too fast. And it helps us for what we're going to do in the following, which is to solve the Eichhorn equation. So what am I saying here? What am I trying to share with you here is that, look, if this is a cosine, x times cosine. So what I'm saying here is that if A is a constant, I mean, if my domain is constant speed, this is actually a solution, okay? The amplitude is constant. The phase is a constant. You're going to see what this theta is, okay? And this is actually what we call, let me put it here, a plane wave solution, where note that the phase, why is this called a plane wave solution? Note that the phase, and here I'm finally going to put the wave vector, which I said I missed it before. It doesn't matter, you would correct it here. Okay, this is actually the same as this too. We can write it like this. Okay. Okay, so what I'm writing here is quite simple. And let me put one more word here. These are plane wave fronts. These guys over here. So let me explain. I was writing right and not explain. So what I want to finish here is put our intuition to work with this geometrical thing. So if everything is constant, right? The medium is constant. The index of refraction is constant. So the wave amplitude shouldn't change. Constant wave amplitude here. Okay? Constant index of refraction. Check on your own that this solves the Helmholtz equation. And if you put little v equal to this times e to the I omega t, it solves the original problem. Piece of cake, easy, okay? But we want to get in more, it's not just checking, right, calculus, differentiating. We're going to start getting our motivation into the application. So this means, look, this means we have a plane wave. So a plane wave, what is a plane wave? A plane wave, first you can see plane wave in many ways, okay? I can sell you the name in many ways. Well, the phase for this guy here is basically this, right? N, k cosine x, k sine x, inner product x, which is xy, the vector x. Okay with the notation? If you're not okay, complain, okay? So, and then divided by k, okay? Because we pull the k out, whatever, okay? So this looks like a plane, right, with a normal vector, whatever. Okay, so that's why I call it plane wave. Another thing I wanted to show is that, look, this is that simple guy we're going to be using over and over again, but this is in 2D, kx minus omega t. And if I pull out, this is a traveling Fourier mode, okay, which I wrote it. This is in 2D, I wrote it over there in 1D. The other thing is that the vector k, if you look at here and here, the vector k indicates, right, if you put this equal to a constant to see what the level curve of the phase is, it's this. So that's why it's called plane waves, right? Or in fronts, the moving front. And actually, if I did this in 3D, it's basically like this, right? Let's see if we can do it. You see what I'm doing? Because here are the points on the crest of the wave. If I were to draw this in 3D, it's not, it's in 2D, but it's just so that we can see. So this is the airplane view of the waves coming to the beach, one after the other. Is that okay, right? And this is the level line for this guy. Put this guy here, equal to a constant, right? You're gonna get straight lines. That's why it's called a plane wave, which is a wave that in this direction, it doesn't change, right? It's just, and we see this in the ocean, we see this in other places. So, excellent, right? We got to a point, okay. We got to a point where we see, from an application point of view, where the Eikono equation comes out. The Eikono equation gives us an idea of how the waves are moving in this region, because the properties of the region can be changing, right? And if we plot the level curves, we get that idea. And this all started from a variable coefficient water wave problem. So in the last minutes we have, let's now get the Eikono equation, constant coefficient, because the variable coefficient Eikono equation is complicated. There's a bunch of numerical methods to solve it, some very sophisticated modern ones, which are interesting, so on. But now let's try to solve the Eikono equation, excuse me, with a constant index of refraction using the characteristics. And there's going to be a lot of interesting geometrical features coming out of that. Let's see how far I can go in this class, and then we'll continue. Okay, so now let's solve constant. What is our Cauchy problem? So we have a Cauchy problem now to solve. Excellent. Okay, for the Eikono equation in some sort of a abstract setting. Doesn't matter. Okay. So the picture is a little bit like this of our Cauchy problem. Right? And we're going to find eventually that we have things like sort of like this. Right? To be seen, right? But the Cauchy problem is this. So we have, so what we're saying is that this guy grows linearly along that curve. Okay, no problem. Well, now let's just forget temporarily of that problem and do just the characteristics, right? So Cauchy data. We have x equal to s. Y, S equals to S, and C equals to AS. Okay. Well, strip condition. We need to complete our initial data, right, for P and Q. So F is equal to P squared plus Q squared equals N squared, like this. And deep C ds is equal to Okay? Now, there's first trick that appears, that this gives us this. Equals 1. And here, we get that d phi dx is A is equal to ds dx, which is 1. So it's going to be P times 1 plus Q times 1. Okay, and I've numbered in the notes the strip condition like this. Equation 1, equation 2. Okay? So as you will see in this problem, we're going to have to live until the end with an ambiguity between P and Q, but no big deal. Okay? We'll see at the end a little more what does the ambiguity mean. But look, with this trick here, I can automatically solve this equation 1 and forget about it by putting a parameter of theta and saying that P is n cosine theta and Q is n sine theta, and I'm done with this equation. Okay? So let's put it here. And we basically solve this equation. And then we're going to carry on this parameter and see what we do with it. But fine, we solved that problem. Okay? So we now get that cosine theta plus sine theta is A over n from the strip condition. That's just this guy, right? Rewriting it. So from here, look, from here we already see a problem, a potential problem. Okay? And we can actually write this maybe in a better way to see the potential problem. This can be written like this, right? The sine plus the cosine, so we can write this like this. Right? I was about to say, I prefer to see it like this. This already tells me a potential problem, which is the data can be bad, right? Because this is physical. If we think this is like an index of refraction. And this was the slope of our Cauchy problem, that if this guy is too big, I do not have a real valued solution, right? This guy is going to be this theta. I don't want complex valued solutions. I want real valued solutions. So we have to be careful in order to get, let me put it this, real valued solution. Right? So let me say it in a physical way. Right here, it's just in a purely trigonometrical way. But basically, if I were to draw this in 3D, which maybe I should have done, and this is AS, right? This is how I'm saying I'm allowing the phase to vary along that curve, right? What this tells me in a physical way, in a purely algebraic trigonometric fashion, easy, right? The sine cannot be bigger than 1. If A is bigger than n, I cannot have a real valued solution, right? But this also, it's interesting to note that this means that if this slope here is too big, right, that means the phase is varying too fast in a non-physical way. that the propagation speed of the equation does not allow. So this guy will tell me that something was wrong, and therefore the Cauchy data is no good. Even not thinking yet about characteristics or anything, right? I mean, just think about the own Cauchy data. If this is too big, it says that the spacing between the phase is on a scale that's faster than the model allows, right? Than the physics allows. So that's bad, okay? So interesting to see that. So, okay. So this is a point, so we have to be careful. And another point here is, let's check condition for gamma to be non-characteristic. Right, which is basically that Jacobian, right? And that is, you can check, be different from 0, right? So I have here in the notes mentioned like no theta different from pi over 4 or so on. No, that's good. That's for you to check. Okay. What should I do next? Because I think I'm not going to have time to finish the whole problem. So let me see what I can do. Yeah, maybe I'll do this geometric thing, which is like the next page in the notes, and then maybe leave to next class for us to solve the characteristic equations. Yeah, let me do something which is good as an intuition and also terminology. Let me call this some facts. Okay. So from this, look, we have that P over n squared plus Q over n squared is equal to 1. That's basically from the PE, right? We also have that P of S is n cosine theta, Q of S is n sine theta. Okay, so that means that our normal vector right, or transpose, doesn't matter. This is our normal vector from which up to the planes, right, which we got the Mond, conj, and so on. Okay, so check this. So I put it like this. Another things like little exercise you can do on your own, please. Check that. We have this. So without loss of generality, I'm looking at things at the origin. Okay, now I have to tell you what I'm doing, right? To be on the honest side. This is 1. So look, what I'm doing is I'm drawing all possible normals. Like thinking of this. right? Because it's n cosine theta and sine theta minus 1. Let's just draw it like this, okay? And then convince yourselves, right? If these are all the possible normals, then let me put it in another color. Right, with say a normal here to this guy, right? Normal there to that guy that we had drew like this, and this is the Monge cone. Right? And I drew in the notes, for example, this is a tangent plane. Right, this is another tangent plane because this is the Monge cone. Right, and this will, as we will see, we're going to solve I think in the next class. Yeah, we're going to solve an Eikonel equation with a singular Cauchy data. That means on a point, not on the curve. And we're actually going to see that the solution at the point is a Monge cone like this. Okay, so this is x, y, z, and therefore we're going to see that sort of information propagates upwards, and this is going to act using the terminology of optics. It's going to also, we can think of it as a light cone. Okay, so how things propagate in the domain like this. Even though propagation here is a little bit of a funny word because we don't have time, right? I mean, there's no time involved. It's not that we don't have time, right? So it basically means this. Look, maybe I should explain this now. So let me use both hands and maybe stop around here. Is that if I have some information here, and this is the light cone, and I do level curves of the phase, remember here that that's the solution, right? So if I put this implies level curve of the phase. Do you agree? So if I cut the cone and I look to these level curves from above, there it's a circular cone, so I see that picture I had drawn before. Let me draw it here. I would see something like this. That's how the fronts propagate, because I'm cutting the cone, and if I look from above, right? So that's for the case of a singular solution. Then using the singular solution, we're going to do a Cauchy curve again using the singular solution. Anyway, but what I'll leave here and do it for the next class is we have not yet solved, I didn't even write, the 5 characteristic equations, right? We already played a little bit with the strip condition, and then we have to find the solution and actually try to see if we have plane waves more or less as I'm indicating here, to be seen in the next class. Because also I'm gonna rush. It's no use. It's good to stop at a good point, sort of revise and start from there. Particularly today's Wednesday, so we start on Monday, right? There's days in between. I have to refresh your memory. So advice is, try to do these things that I'm doing in an incomplete fashion. Do it at your own, in your own way of thinking, right? So that you can practice, and that's the best way to understand what's happening. Okay? And maybe this is a good point to finish. Obrigado.